We know h of 3 equals -7, and the derivative at 3 is equal to 1.4. You were supposed to do this problem, so make sure that if you haven't, you push pause and do it yourself. But I will go ahead and do all three of these approximations. Now, we don't know what the function is, but that's okay. I don't need to know what the function is in order to do approximations. I just need to know that at the x value of 3, we're at -7, and then we are currently increasing at a rate of about 1.4 units in y per unit in x. So if I want to approximate at an x value of 3.2, I'm going to take the output when I plug in a 3, and then I'm going to add 0.2 times the derivative at 3. I'm going to write all of these things in one line. So we end up with -7 plus 0.2 times 1.4. If you take -7 plus 0.2 times 1.4, you end up with a -6.72. So the approximation of h at x value 3.2 is a -6.72. When we want to approximate h at an x value of 3.05, we do the exact same thing. We put in the output of h at 3 plus 0.05 times the rate of change. So that's -7 plus 0.05 times 1.4. And you end up with a -6.93. Lastly, we approximate when x is 2.95. So we take h of 3, and we're going to subtract 0.05 times the rate of change. When I type in that, let me rewrite that. So when I type in that, in particular, when I type in -7 minus 0.05 times 1.4, I get a -7.07. Let me rewrite that because this, when I typed in the 3, it kind of showed up ugly. And I'll write in the intermediate step as well. So -7 minus 0.05 multiplied times 1.4. And that gave me a -7.07. Now, as far as how well these functions approximate these values, or how these approximate values, how close they are to the real values, depend on a couple of things. It depends on how close the x value is to the x value I was using to approximate. So in this case, 3.2 would probably give me a good approximation, but 3.05 would be even a better approximation because it's closer to 3. So that's one thing it's going to depend on, how close you are to the value. It's also going to depend on just the overall shape of your function. So the way I like to say it is the derivative is giving you speed, but how the speed is changing, if this speed is changing very, very quickly, then the approximation is not going to be quite as good as if the speed is changing fairly slowly. So you get better approximations when you're close to the x value and when the rate of change does not change very quickly. We have seen now how you can approximate using the derivatives. You can approximate where the function's going to be by using the derivatives. And you might not think that's a really interesting task, but this happens all of the time in real world applications. Imagine you're trying to pick a stock and you're trying to figure out where it's going to be. There's not going to be a nice function that you're going to have for a stock price. It's going to be jumping all over, but what you will have is you'll have its current price and maybe a general idea or a good approximation of how it's changing at this point in time. So if you know those two things, you can approximate what it's going to do in the next week, in the next month, et cetera, et cetera. So if you know where something's at and you know the speed, then you can approximate where it's going to be at. Or take another example that we saw earlier. We know that rates of change tell me that if I have a position function, the derivative is going to be a velocity function. So what you could do is you could figure out in physics where an object is located, how fast it's changing, and then you can use that to predict where that object is going to be located in the future. So think about asteroids and things of that nature, where it's located, what the rate of change is going to be, and at what point in the future is it going to be at a certain location. So all kinds of really interesting applications with that approximation of the function's value given where we're at and how things are changing. So that is the end of section 2.2.